Good afternoon, everyone. This is Tim Welp, and today I'll be kicking off this technical discussion on updates and innovations on sand bypassing systems that I'll be presenting along with my good dredge buddy, Zach Tyler. Got a question? You could either send it in the chat, or we'll take them as they come in, as long as we don't exceed our time limit. So today we'll touch on some background terminology to set the stage, and then get into the meat and potatoes of updates and innovations on today's sand bypassing systems. What we want to do is to give you an idea of how much sand bypassing technology has changed over the last 2 decades or so. And so we have a relatively large number of detailed slides that you can use for reference later, because the PowerPoint presentation will be on the SERP website. During the presentation, some of these slides will briefly touch on certain aspects, just to emphasize certain points of this technology. So, as we all know, the U.S. Army Corps of Engineers dredges in a lot of different types of water bodies to achieve our navigation mission. We dig in rivers, estuaries, bays, lakes, etc. But out of all of these different waterway types, inlets are one of the most dynamic environments that we have to work in. So here we have an aerial photograph of the Indian River Inlet in Delaware back in 1931. And that's beautiful. Shows how Mother Nature abhors straight lines. But imagine being the skipper on a shrimping boat trying to get back inside and navigate through that. So along comes the Corps doing what we do, and with straight lines, I might add. You can see in this 1935 survey that in order to stabilize the inlet to enable a safe trap passage for that shrimper we're talking about, we're proposing to build new jetties. That we did 3 years later, as you can see in this 38 aerial. It still shows relatively uniform coastline around the jetty flanks. But when we fast forward in time, as you can see in this 1968 shot, starting to mess with the system's dynamic equilibrium, where sand is starting to accrete on the south side and erode on the north. Time warp forward, 1988, and that accretion erosion difference is even more pronounced. So in order to mitigate this impact on the movement of sand, we bypass it. For this presentation, we'll be using the Coastal Engineering definition of bypassing that you can see here, where it's the mechanical transfer of sand between the inlet and or adjacent shoreline to minimize the inlet's erosive impact to adjacent beaches. We'll also throw in the backpassing definition, where it's the transfer of sand from the inlet shoals or some portion of the shoreline to, as per the CEM, the shoreline from whence the sediment came. Now it comes to classifying these different types of bypassing systems. We're going to use the CEM's degree of mobility criteria, fixed, mobile, and semi-mobile categories. So fixed systems include configurations like a jet pump inside a structure, like the one at South Lake Worth plant that Zach will be talking about later, or with one with jet pumps on a pier, such as at Narayan, that Zach will also talk about. Now, mobile systems include dredges and shore-based equipment like front-end loaders and trucks. And then you've got the semi-mobile plants that are kind of in between the fixed and the mobile systems, and with an example being like a jet pump on the end of a crane at the Indian River Inlet, where that excavation point can be deployed at one location at the inlet for a certain amount of time, and then it can be moved to another location while still at that same inlet. So let's say you've got sand and an inlet arc where you have the downdrift erosion problem and or a lot of shoaling in the channel, and you want to find out what's the current state of practice or the state of art technology, so it can help you make that decision on picking the optimal sediment management solution for your inlet, and because all inlets are unique. Well, you go off the subject matter, you're going to be disappointed, because the readily available literature is extremely dated. sand bypassing system selection EM back in 1991, and we're going forward to see the Coastal Engineering Manual, Chapter 6, was published in 2003. So that's why SERP's preparing this technical report on the sand bypassing, because we want to give the reader current information on what's being used in the U.S. as well as overseas. And Zach and I are still putting together information that's trickling in from the different sources. So if you see something we're missing or got something wrong, please let us know ASAP. And our email addresses are on the cover slide. I know, if you have this inlet back sand, then inlet problems probably lack of sand where it's needed and sea level rise. So now we'll get into the meat and the potatoes of the bypassing. The majority of sand bypass in the U.S. is done by dredges. So what we're doing is we're going in and updating information on select bypassing projects that use these different types of dredges. And here you can see an example of the different dredging projects that bypass sand, as well as the general operating parameters that we're looking for. And some of these projects, nothing's really changed over time except maybe the price per cubic yard. And we're finding out that getting this information is taking more time than we thought it would, because the databases we've used so far don't have the fidelity to tease out the yardage and cost numbers. So we're doing the snail mail and email and calls to get the specifics. What we did find out on an update on the Port Canaveral sand bypass project is that the Jacksonville District is currently investigating potentially merging this bypassing project with another nearby federally funded dredging project to reduce the mobilization and demobilization costs. And this could very significantly reduce both projects' overall cost per cubic yard. Now we're seeing, as we're going out doing the survey, some inlets bypass sand with dedicated dredges. And when I say dedicated dredges, I mean that the dredges are used at the inlet and they stay at the inlet. I think what we've got, Hillsborough Inlet, Florida, Santa Cruz Inlet, California, and Baton Rouge Inlet back in Florida. Each is just an example to show you, but the Hillsborough Inlet District has been dredging since 1961 with an Ellicott dredge. The dredge is getting old, more too expensive, so in 2008 they replaced the dredge with another Dragon series, larger dredge, 14-inch suction, 12-inch discharge, for a price of $1.8 million. And you see in the slide some of the key dredge features that are included, and basically all these are to enable the Hillsborough Inlet District to be able to dredge safer, faster, cheaper, and greener, so to get their operation optimized. Now, what we're also seeing is that the method of placement, we're seeing increased use of nearshore nourishment. We'll place the sediment close to the shore, but in the water, to keep that sediment in the littoral system and keep some of that sand up on the beach, but keep it in the beach profile. And in previous SERP technical discussions over in the Regional Sediment Management Program and the Dredging Operations Environmental Research Program, all of these programs are orienting, developing, doing R&D and developing projects to further promote this nearshore nourishment that can be more economical and in some cases more environmentally safer. And it just here's using this as an example, Fort Myers Beach, Florida, where basically they had an 18-inch cutter head dredge the inlet and pump it about 1.5 miles into the nearshore placement area and about 4 to 6 feet of water, and be able to practice that nearshore nourishment. And another, we're seeing more and more of the nearshore nourishment, and this just came on the radar where the Mobile District and our Regional Center of Expertise got together, and they did what they're calling an in-channel sediment placement in the Pensacola Pass Federal Navigation Channel, where they placed sediment, first they analyzed to see where the sediment, to predict where the sediment would go, but they placed sediment in the hallway, the deeper spots of the channel and the inlet, and right now they're monitoring the project to ensure that the sediment is going out the inlet and back into the little process. Now we're going to go from a mobile system to a semi-mobile system. Talk about the Indian River Inlet and bypassing plant, where they have a jet pump on the end of a crawler crane, and they're pumping the slurry up over the bridge with the pipeline mounted under the bridge and onto the North Beach. Here's a hydraulic hydraulic circuit diagram. It's designed to pump about 170 cubic yards an hour. Goes 100,000 cubic yards per pumping season. It runs from Labor Day to Memorial Day. The plant was completed in 1990 at a cost of $1.6 million, dated 1990. And right now they're getting a cost per cubic yard approximately $6. Here's a picture of the jet pump, or some people call it a ductor, on the end of the crawler crane, indicated by the red arrow. So yeah, I'm going to spend just a little bit of time on it because the number of the following slides are going to talk about jet pumps. The jet pump works by providing high pressure water into the supply water, or some people call it motive water. Certain volume is branched off for the fluidizing jets. The remaining high pressure water goes through a nozzle. It increases the velocity such that when it gets into the mixing chamber, it exchanges that momentum and fluidizes that slurry of sand and water, such that when it goes into the enlargement section of the pipe, that velocity energy is converted back most into pressure, and it goes, the slurry, the sand, and the water go out through the discharge. The beauty of this type of pump is that it has no moving parts. Here's a picture of the jet pump on the crawler crane excavating the crater in the swash zone. Over the years, they've upgraded the production measurement instrumentation with the select pieces you see here in the slide, as well as when they built a new bridge, they updated the pipeline section going over the bridge such that all the metal pipe and elbows of basalt line to combat the abrasive nature of sand and extend the useful life of the pipeline, as well as, interestingly, because of the expansion and contraction of the bridge, they had to put an expansion joint in the pipeline, which I've never heard of before, just to be able to flex with the bridge. Current update: the Philadelphia District is currently working with DENREC to extend the local cooperation agreement that's expiring in 2021 to extend into the future. They just completed a major refurbishment of the crawler cranes so they can handle basalt corrosion better, as well as they're currently working on replacing their original diesel engines with electric motors to power the pumps. Now I'll turn it over to Zach.
Thanks, Tim. So I'm going to have a quick review. I'm going to do a quick review of the three locations, case studies for, first one is in South Lake Worth, and then we'll jump over to Australia, talk about Nerang and Tweed River sand bypassing plants. All three of them are fixed plants. This picture here is of South Lake Worth, and you can see that they're doing some construction. They got some sheet pile around their sand bypass building. Next slide, please. So this is what it looked like when first installed. The sand bypass plant was pretty small down here, built in 1937. And it's a pretty simple system, having it run a pipeline discharge to the other side of the beach to try and mitigate some of the secretion occurring on the updrift side and the erosion occurring on the downdrift side. Next slide. So this is kind of the worst case scenario for an inlet when a storm comes by. This is South Lake Worth. You can see here, this is probably a non-navigable inlet until it is dredged, and it shows the reason why you might like to have a sand bypass system installed. Next slide. So originally, pretty small system, 8-inch suction pipe with a 6-inch discharge and a small 65 horsepower engine. They were able to achieve about 55 cubic yards an hour, which is pretty decent for what they were working with back then. Between 1937 and 1941, their average rate of bypassing was about 50,000 cubic yards per year. Next slide. So in order to kind of help keep up with the amount of material accumulating in a channel, they decided to upgrade the system in 2009. This is just pictures of the system being upgraded. This upgrade helped tremendously with reducing the amount of maintenance necessary for maintaining the equipment, the pumps, and all the electronics. Next slide, please. So they went on to a 14-inch suction pipe with a 12-inch discharge, and they looks like they did 10 times the horsepower with 450 horsepower, and they got the production rate up to 150 cubic yards a year. And when it's working, as of 3 days ago, it's actually down. According to a recent news article, they make 75,000 to 80,000 cubic yards a year. Next slide. So this is just kind of tracks how they've been, this graph on the bottom right tracks how the production and the amount of power they've been using has changed over the years. They've had multiple upgrades and some efficiencies. They've had higher, in the early 2000s, pretty high. Their record production rates, but they dropped off recently. That's due to just how they're operating the system. On average, they're nowadays doing about 200,000 cubic yards per year. Next slide. So moving over to Australia, this is a view from the updrift side of the Nerang bypassing plant. What you're looking at in the kind of foreground is the pier, about 900 meters long, not 300 meters long, excuse me, and the inlet. Next slide, please. So just some background information. The 1983 aerial image of the Nerang system that shows that it's pretty complex tidal inlet. 2009, significant, or in the 1980s, significant construction was performed, lots of seawalls, jetties, and the sand bypass system was installed. And so they've effectively gained some degree of control over the navigability of the inlet here. So it was constructed and it was commissioned in 1973, and Delph Hydraulics provided a lot of the technical guidance for the Gold Coast waterway. They did a physical model, which you can find a documentation on the pre-construction conditions. Cost $5.3 million to build, $1986 US. It has 10 jet pumps currently. It started with 9, I believe, but now it has 10. And currently doing 600,000 cubic yards, 650 a year. Next slide, please. So just a sort of a close-up view of what's going on. This is the largest sand bypassing system. The pier is a red line, and with the yellow dots being jet pumps. And you can see they bypass by going underneath the channel. They have a steel pipe they've run underneath the inlet, and it discharges on the downdrift side of the inlet. Next slide. This is just a cross-sectional view of kind of what's going on at Nerang. You can see the jet pumps below grade, and the various sources for fresh water and discharge water. Next slide. So the big thing that they've had to overcome back in the late 80s, early 90s is basically the debris problem. The Nerang River often is flooded, but when it is flooded, there tends to be a lot of debris in it, and they've had to make some adjustments, basically increasing the size of some of the components of the system. But it's been to great effect, and it has increased how efficient they are and how often they can operate. Current good production for them is about 525 cubic yards per hour. Next slide. So they've electricity power is an electrically run system in Nerang. It's a little bit more expensive in Australia than in the U.S. So they typically run their system at nighttime and continuously over the weekend. So from Friday evening to Saturday or Monday morning, they run it. They've done quite a bit of kind of development in materials for all the components of the system and the pipes and the pumps and everything. And so working with them has been a wealth of information concerning the materials required to perform this over a long period of time. Next slide. So this is just some pictures of what they're kind of doing nowadays. They're currently upgrading the strength of the jetty to steel jetty, so they're kind of reinforcing that to support their operations there. A larger crane to do maintenance on all the pumps. They periodically require maintenance. On the left side of the page, there's a picture of what one of their jet pumps looks like. That's a GenFlow jet pump. You can see it's very similar to what Tim showed a little earlier. Next slide. So, like I mentioned, they're constantly upgrading the system. In addition to upgrading the jetty itself, they're also upgrading the power distribution system. And circle down at the bottom there is how much they're putting into it. Just for the power distribution system, it's 1.6 million Australian. So probably a little bit more U.S., probably closer to 1.8. Next slide. One of the things they've recently done is pretty cool, is they've installed a solar panel array, which is paying dividends by reducing their energy costs for running their shops and their maintenance. They currently do not use it for operations, though, and they're very cognizant of their carbon footprint, and it's helping reduce how much carbon footprint they're producing, and they're very open about it. They have an app. On the next slide, we'll talk about their app. But they've been very successful with the solar panel. Only been there about a year, but they are generating about 600 kilowatt hours each day. So that's taking a big chunk out of their operating costs. Next slide. So we skipped straight to Tweed River. There must have been a slide miss there, but they have an app, and it's really great for helping communicate with their community how much production they got, how much energy they're saving with their new solar system. So they're very proud of their system. But we'll move on to Tweed River. Tweed River is sort of nearby Nerang. Both of them are south of Brisbane, Australia. And this is Nerang's sort of baby brother, built a few years after it. Next slide. So they started operation about 20 years ago in 2001. Their jetty is just slightly shorter at 1,480 feet. The other jetty was about 16, I believe. So it's a very similar system, as I mentioned, 10 jet pumps with 4 working at any one time. They can adjust which set of 4 depending on where the sand is currently in the accretioner fillet. Annual production rates from the duration of their operations has been about 660,000 cubic yards per year. Similar to Nerang, it's pumped underneath the inlet, but in this system, it's not one distribution point. It follows a network of discharge pipes to 3 different placement areas. Next slide. So something I didn't mention from Narang is that their sand bypass system is almost completely reduced their need for dredging the navigation channel. They've dredged once in its 35 years. But that is not necessarily true for Tweed River. It's just a different animal. It requires periodic dredging every other year or so. And they typically use this trailing suction hopper dredge, albatross. And their placement areas shown in the map on the left is very similar to their discharge areas. So they place in the near shore, and it's been a very successful kind of operation for them. Next slide. So in order to monitor their production rates in the discharge areas, they set up an Argus system. It's been on and off for the last 20 years or so. It's currently working now, in the Water Resources Laboratory over there is the kind of a data holder. And they use this information to help communicate with the local agencies and community on what's going on with the system and how the beaches are responding to discharging material in the near shore. Next slide. And Tweed, very similar to Narang, has an app as well, and their app's pretty high speed. So it tells you everything about how much is being pumped and how much is being dredged and what the conditions of the entrance is. And it's also a way for the locals to view the surf report so they can look at cameras of surf for all the surfers out there. Next slide. I think that might be the last one for me. No, one more. So yeah, they're pretty cool. They're Australian, so they're all very cool. And they publish like a magazine on their operation there, and you can see on the right they kind of keep track of all the things they suck up with their system, and surfboards, fins, sunglasses, everything. So they're pretty open about what's going on with the system, how it operates, and what they see on the day-to-day, it sounds like. Next slide. Yep, so that's you, Tim.
All right.
Thank you.
Exactly. All right. Now, we just recently found out about this as we're boring down into the Tweed River plant, is that there is even a smaller jet pump installation on a piled jetty at Nakura Industrial Port Sand Bypassing Plant in South Africa at Algoa Bay. As you can see the picture in the foreground, you can see the jetty with the jet pumps on it, where in this picture it's not so good, but pulled it off the internet. The similar dots that Zach used for Narang. You can see the jet pumps. They're pulling the clean water, motive water supply from the port and powering the pumps and then discharging it around the port, and where they're placing it on the north side of the port. This was construction started in 2002 and it's commissioned in 2007. It's got 6 jet pumps mounted on a 740-foot long jetty, and they're pumping a distance of about 11,155 foot. And they need to use 3 booster pumps to get it that distance. And typical pumping capacity is about 400 tons per hour. It's monitored and controlled by a PLC system, and they pass about 240,000 tons of sand per year. Like I said, we just found out about this system, and here's a couple pictures of the jetty, as well as this is the crater being excavated by the jet pump. So trying to find out more about this system, and supposedly, if anybody else knows about it, there's supposed to be 2 other systems, one in South America and the other one over in Japan, but we haven't been able to ferret out that information yet. This is Swash Project Delivery. It's a website over in Australia where they are ahead of us in indexing their sand bypassing systems, and I could spend 5 to 10 minutes on this alone, where they have categorized and classified their different bypass systems with the excavator and jet pump, similar to the Indian River, pumping jetty, like Tweed and Narang, using excavators, dredges. We've got it all categorized. And it's interesting, in 4 locations, they're using technology called the sand sifter. And we're trying to dig for more information on this, but basically it's a fluidization shroud that starts on the surface of the sand in the swash zone. It fluidizes the sand, and we think it uses a jet pump to suck the sand and get it fluidized up into a shore processing plant. And on the right side, you can see a picture of this crater that gets excavated by the sand sifter technology. And like I said, there's supposedly 4 installations in Australia that are using the system. But also in America, we have a similar system that Zach and I got to work on with the Galveston District and as well as the Galveston Island, city of Galveston Island, where we're using the Bedload Collector technology. It's basically a hopper installed down in the swash zone, where we did some field tests, and we're going to get funding to proceed in the pilot project. And COVID hit, and the project right now is suspended. And in America, we also have what's called the Fluidized rock system, which if you have debris and you want to get the oversized debris down to about a 3/4 inch oversized screen, this might be a system that you'd be interested in. Basically, on the left-hand side, connects to hydraulic dredge discharge pipeline. Basically hits a scalper to bleed off the energy, and hits 2 vibrating screen trays, like I said, down to 3/4 inch. And the cleaner slurry goes out on the beach, while the oversized will go into a bin or into some all-terrain haul trucks. And here's just an example: beach nourishment on Treasure Island, Florida, done by SAJ in the state of Florida. Arrows indicating the cutter head Norfolk. It's like 32 inch cutter head, dredging the inlet. And this is just an example of the oversized debris that the system is separated from. It can handle up to like 40,000 gallons per minute, which is what the Glen Edwards would pump ashore for a hopper dredge size. There's also, in Australia, they've got a variation of this to where in Mandurah and Dawesville, they'll take a front-end loader and excavate dry sand, place it into a hopper, fluidize it. This is all track-mounted. They'll fluidize it and pump it either to a bypass situation or a back pass situation. And supposedly there's 3 or 4 different projects in Australia that use this system. And then in closing, how many coastal engineers and civil engineers have been traumatized by the infamous Miami Beach photos of the erosion, bypassing or backpassing? Common denominators. You have a lack of sand where you want it. What the Jacksonville District did was a variation of that crawler-mounted fluidization hopper, where the SAJ Dade County Beach Erosion Control and Hurricane Protection Project, they basically dry excavated the sand with front-end loaders and the dump trucks, dumped it by this fluidization hopper, loaded it with a hydraulic excavator. And you can see the pump here where they added a clean water from the surf zone, and they pumped the material, and they back-passed it from an accretion zone to an area that was an erosion zone. We just wanted to do this presentation, hit a bunch of slides real fast for you, but just to demonstrate how sand bypassing technology has changed over the last 2 decades, and that if you've got sand and an inlet, that you have more options to hopefully apply an optimum sediment management technology. Thank you. Questions?
All right, yeah, we'll take questions. You guys can unmute yourself. You can hit *6 to unmute in the app and also your phones. And the chat is also available.
Hey, Tim, Zach, it's Rob Moritz. I really like the last image of the back passing. That seems really I kind of an interesting turnkey way of handling. A lot of times, I've worked on projects where backpassing ends up being such a logistical challenge that the project doesn't work. But this does look very workable. My question is, you showed a lot of different locations of bypassing and backpassing in the world. What were the general unit costs for each one per cubic yard? All told, the sunk costs, the effective unit costs. Over.
Well, okay. So right now for the dredging costs, we'll just start with the dredging costs. We're trying to use the dredging information system and calling the different districts as well as the private inlets. But what we're seeing for the Glasport Canaveral Sand Bypass project, where they're paying about $12.80 per cubic yard, and similar, for size product, like the Channel Islands out in California, when they move about 1 million cubic yards, they're paying $8 a cubic yard. And like I said, these are preliminary numbers, and that's why I specifically mentioned during the presentation that as we putting this together, we're going to send out these numbers back to the organizations that gave them to us because of the sensitivity in numbers. Do these numbers include mobilization, demobilization, permitting, et cetera, et cetera. What we saw was for the dedicated dredges that for right now, the numbers that we have for what we gave you, Hillsborough, we pulled their numbers off their dredging for that right now, that 14 or the 12-inch Powderhead dredge. They're pumping about $13 a cubic yard. Then you go out to, say, Santa Cruz, where they bought a new dredge back in 2016. They're pumping it for $5.86 a cubic yard. So these are the types of questions. What are the background parameters? Why, and we haven't seen. Usually, if you got a bigger project, the cost per cubic yard goes down. We haven't necessarily seen that trend in the projects that we've done so far. And all those projects over in Australia, we ask them and they won't give us costs per cubic yard. So the cost is it's one of the most relevant parameters on the feasibility of that type of bypass, the backpass technology, but it's hard as heck to get those numbers and to get them on oranges to oranges and apples to apples. Over. I'm sure I can give the people at SAJ a call and find out what their numbers are for the Dade County project. All right, Kevin? Any more questions?
Well, if no one's going to bring anything up, this is really important. I think that Jim Clausley did a lot of good work. He kind of ran the sand bypassing work unit for a while. He kept it infused with interest, but since Jim had retired a few years back, it's just his appearances. It seems to kind of like gone into the shadows, but it looks like you and Zach are going to resurrect it, and it's very applicable. The thing about cost, this is really important. It always is. It's all about money. There's an RSM, a little RSM project that Portland District did that looked at the unit cost savings for different ways of managing dredge material placement for nearshore placement. And we were looking at more of the operational savings in terms of hauling this stuff, this nice clean sand, to deep water sites versus spending a little bit more time or apparently spending a little bit more time to place it near shore. And it turned out that we actually saved money by going to the near shore because it's a slightly closer location. So it's an increment on the overall operational cost savings, but that's on the operational side. On the placement side, it seems, when we compared $6 a yard, $12 a yard versus what would it cost to get that same sand from a terrestrial source? Okay, so that's cost differential there, and hopefully savings. But then more importantly, what's the benefit per cubic yard placing on the shore like this? The Miami Beach thing, I mean, holy crap! When they rebuilt that beach, it changed the entire Miami tourist industry. It changed that. It revitalized it. The river benefits are huge. So I think to tell this part of the story is the technology to do bypassing, but the benefits of it, both operational and cost savings, and the benefits to the place. It's just Miami Beach is astronomical. I mean, anyway, I'll send my piece. Thanks, and I yield back the balance of my time over.
No, thank you, because when we were trying to, on that slide where it said that we're increasing the use of nearshore nourishment, we were looking to, because that's a ballot, that's a way that the Corps and stakeholders are changing the way that they bypass sand, and it's relevant, and to be able to quantify it, so measure the benefits and the costs. I'm going to dig up that RSM report that you prepared, because it's like I said, follow the bucks, because it makes all the difference on the feasibility of the technology. Thank you.
Hey, Tim, this is Tanya. Can you hear me?
Roger.
Hey. So, which all districts have you been in contact with about, either their interest in these types of sand bypassing, backpassing systems, and I guess what's the level of interest for any needs on the R&D side? Because I'll note that, you guys started looking into this in the past 6 months or so to try and get an update started for the program, but this wasn't a listed statement of need. It's more just, there's been a dearth of information since, as Rod pointed out, Jim Klausner's retirement. And so, it's good to get some of this information out there, even if it doesn't have the nitty-gritty financial numbers associated with it. There's just a lot to share. And I'm kind of curious, if you got any feedback from folks that you talked to across the Corps about interest for any other needs in the R&D side.
We have talked primarily with the Los Angeles District, Philadelphia District, and then the Jacksonville District. And for the Cape Canaveral's a big sand bypassing project, and they were looking, at all the alternatives I mentioned, merging the North Reach dredging project with the sand bypassing project to lower the demob costs, and that's where they've expressed interest in looking at alternatives. But just we're collecting all the information right now, so when we in turn send out the draft for their review, that's where we'll be looking to gauge the responses to these alternatives and their applicability, because the majority of the rock fluidization system projects have been done in Florida, so that we have not reached out to north of the northern coastal core districts yet. Get your response.
Hey, Tim and Tanya, this is Marty Durkin in Jacksonville. If there's time, can I have, I guess, a comment or some input along those lines?
Yes, absolutely. Go ahead.
Can people hear me? Yeah, so I'm the planning technical lead for an ongoing feasibility study for Miami Beach, where we see the pictures up on the screen. We're currently, so our TSP milestone is currently scheduled for August 2021. We're looking at, several alternatives and, currently working on some cost updates for several options for, in the middle picture there, you see, just south of Baker's Hollover Inlet, at, a fixed sand bypass plant, also looking at trying to work up some costs for getting a, project-specific type dredge that could bypass material efficiently there. And, something we're seeing now with one thing in this area, there's scarce, big quantities of sand, offshore that we can get economically. Truck haul is pretty expensive. And also just, doing sand bypassing with a contract now to dredge every time you need to do the work, we're seeing mobilization costs in like the, $5+ million range every time you need to mobilize a dredge to get on site. So those are a couple of the things we're looking at, as well as the back passing from South Beach. And, I've reached out and got some good information from Jeff Gebert on the Indian River Inlet and some others in Philly District on their operation there, and got some information on the Rudy Inlet project from Norfolk District. I guess that's a local project, but they have a, on-site dredge. So we're looking into, some options like that. And, some things that we're trying to consider too, or need to take into consideration, is doing this type of operation on a, high density population, touristy beach area. Earlier, or I guess last week, we were on a call and, talking about these things with our sponsor, and they were talking about, the last backpassing event. People are still complaining about, the dips in the beach from the holes where they got the sand from, and back passing it is still ponding with water, at certain times. And it's tougher where a lot of like the stuff in Australia and stuff, you've got, pretty undeveloped coasts, and even the Indian River project, it's a, big park. So considerations for people wanting to use the beach without interruption. And also, with the consideration for the environmental impacts to nearshore hard bottoms in the area. So if there's, technologies that can get the sand in the nearshore, near hard bottom areas without causing a bunch of turbidity, that would be, interesting stuff to look into. Sorry, that was kind of some long rambling input, but that's kind of what we're looking at for this study now. And, we'd definitely be interested in staying in coordination with you as we move forward and get some of our costs developed, and see if we can achieve some efficiencies with bypassing or backpassing for this study moving forward.
Man, you just ran down in the coastal or in the old engineer or the sand bypassing engineer manual, just how those social and economic parameters, well, you may have the best engineering, most economical and environmentally acceptable solution, just how the social impacts have to be accounted for, because you can't necessarily pick the most efficient system because the other parameter or criteria outweigh the selection. And we'd be very interested, because as we get more information on these other systems, to share with you, as well as I wish that Bedload Collector system pilot project could have moved forward, because Galveston Island had similar concerns as a lot of people on the beach, and how you gradually take out, because it was envisioned, because the Bedload Collector has been used in riverine applications. It's a proven product, but in the coastal environment in the swash zone, it hasn't been proven, but that's where we're interested in the sand sifter to see what kind of production numbers you get, because you take the sand out in an interception mode where you can't take it out quicker than the swash zone moves it. And it was interesting because in the Rang, the jet pumps in the jetty, the 4 jet pumps that are most shoreward facing, the closest to the shore, have like 2/3 of the production of the entire pier. So the swash zone is happening in place, and maybe, you know, I wish I could give you parameter production performance metrics on the Bedload Collector, and that's where because we didn't get a chance to do the pilot project. But that other system that we're stored in the swash zone, the sand shifter, that's we're proceeding because the same people that built and designed the Narang bypassing plant also have patented this sand shifter technology, and where it bores, and you saw that crater that it made, but the Bedload Collector just sits there and the sand drops in by gravity as opposed to the fluidizing system going down into it. So we'd love to work with you. Like I said, this is and Jim Klausner was my mentor, and like Rod was saying, he was pushing the sand bypassing updates, plants updates, and you know, to be able to get this kind of information available. They actually had a database of the different plants. So in the future, as you move forward, if we can work with you to get you a better solution, sediment management solution for your project, we'd love to.
Yeah. Thanks, Tim. And one other consideration that I think makes, or maybe kind of makes bypassing or backpassing, I guess, a challenge for USACE specific projects, you know, where we're coming up with a plan with our sponsor, and with a backpassing plant or, you know, physical, I guess, equipment like that, you know, that becomes part of the project, will cost share in the initial construction, but, you know, per our policy, it's then all on the sponsor for all the operations and maintenance costs. And so, you know, I guess what we're trying to find out with our analysis for Dade right now is what, regardless of who's paying for it, what's the, you know, most economical plan for over a 50-year period of analysis. But if the bypass plant comes out to be cheaper, we're probably going to get some pushback from our sponsor, when it might be the case that because of how our cost share policy works, it might be more money for our sponsor to operate and maintain a backpassing or bypassing system like that than it would be for them to just cost share in beach nourishment, where we're contracting out a, you know, dredge for each nourishment cycle, even though the overall cost is going to be more. And it might be more, you know, just burden on them in general, keeping up with all the operations and maintenance. That's just another, I guess, thought for the group.
Oh, I have never thought of it like that. And these observations, I'd like to, you know, work with you just to include in this report, just the considerations, because how that cost sharing is structured. I mean, again, all these factor into what's the best system for you versus what's the socially acceptable and the economical system. So that's an excellent. Thanks for bringing up that consideration, because I never thought of that before. And it's definitely going to make a difference to your stakeholder.
Marty, this is Kevin. I think that's a great point, and just for your consideration, maybe tie that to Baker's Hall River navigation channel to alleviate that concern a little bit.
Yeah, so I mean, I think in general, if there's Section 111 considerations for the inlet where the sand's being bypassed, that would help that situation. Where maybe we could still help cost share in the bypass plant, but I'll follow up with you on that, Kevin, because Baker's Hall River's got a kind of convoluted Section 111 history where it's not really applicable there.
Yeah, gotcha. But yeah, nonetheless, it's a great point by you.
Yeah.
Canaveral Harbor would be on the other side of the fence, right, since it's a navigation feature.
We have time for another question or other comments.
Hey, hi. I don't want to preach anymore, but we got to pound the benefit to get to the federal interest. With the headquarters directive now that we fully consider all 4 accounts for estimating benefits for federal interest. There's a rich treasure trove of benefits out there for actions like this. We just need to be creative, exploitive, and push the boundaries on it. And really, I'm a big believer in guidance, but I'm also a big believer in guidance evolution. And guidance won't evolve for our current situation until we push the boundaries. I mean, get those benefits, space and time. Over.
As always, Rod, you bend my brain. Guidance evolution. That's a new one. It's good.
Well, Kevin Hodgins had a question about the 4 accounts federal standard. It's just the least cost. There's a consideration of benefits in the costs margin, and there's costs, least costs, but there's also the acceptance of or the acquisition of benefits for the benefit to cost margin. That has something to do with project selection. Kevin, you want to opine on that? Over.
Yeah, Rod, I was just kind of curious your thoughts on how, this new memo might affect how we treat the federal standard, and I know it's not really treated universally across all districts. So, yeah, it's interesting if it is specific to least cost, and when we say least cost, do we also bring in environmental costs and social costs of the operation? Over.
Yeah, good point. I'm not saying all this is easy, but you see, sand is a very important resource, and a lot of our projects, CSRM and other derivative benefits for federal interest, tie right back to sand. And it's, I'm just saying, headquarters has given us some ammunition. We've been in previous CERB meetings and CWG meetings, we've talked about, hey, what can we do to try to get a handle on more benefits? Not just incremental benefits, but project-specific, justification direct benefits. And so headquarters responded with the 4 accounts that you shall. It's kind of like a directive. Oh no, we got to do more stuff. No, it's a directive to say you want it, you asked for it, now you got it. We just need to be creative within the guidance, and then we can do more with sand. Over.
Yeah, 100% agree. It's like a golden egg, and it's up to us to take advantage of it and make a solid case for what we want to do and send it up the line.
Thanks everybody for the good discussion. We're at the top of the next hour, so we're going to go ahead and wrap up and thank our speakers. I would like to thank Tim and Zach for all the work you've done putting together all the information you have. I know you guys are working on this technical report, and we're again, looking to facilitate getting that information back out to you in more ways than one. So, one thing I'll suggest is Zach and Tim is to consider bringing this up within the Coastal Working Group and maybe other COP venues. And it would be nice to have it, shadow maybe one of our core projects that's looking at one of these capacities and look at it from all those different angles that have been brought up today and give it a little more context for discussion and ways that we might, demonstrate these projects' benefits. And So I'll be working with Tim to kind of scout that out. But please do feel free to get in touch with Tim and Zach on the subject. They're working hard on it, and we are looking for feedback and collaborators. So thanks again, Tim, Zach. Great talk today. Appreciate it. Appreciate y'all for joining us.